Section 5.5 describes the permutation feature importance model agnostic method, which measures the increment in the prediction error of the model after the value of the features are permuted or randomly reordered, which is done with the purpose of breaking the relationship between the feature and the true outcome. The concept is very simple and straightforward. Usually, we start training a model with training data, and then we can measure the generalization error using the test data. This is done using a loss function, such as mean square error or mean absolute error. In this method, the importance of a feature is measured calculating the increase in the model's prediction error after permuting the feature. Permutation is defined as the action of changing the arrangement, especially the linear order of a set of items. In this case, the values of the feature are randomly shuffled. We can see in the figure that we have a trained model. And then we start by permuting the values of feature F1. After this, the model error is estimated using the permuted dataset. If the value of the new estimated error is greater than the original estimated error, a feature is considered important, because in this case the model relied on the feature for making predictions. Conversely, when we shuffle the values of feature F2, the estimated error of the permuted model remains unchanged, which means that the feature is considered unimportant, because in this case the model ignored the feature for the prediction. Here we can see that the feature importance can be calculated using either test or training data. Later we will discuss about this. This technique was introduced by Breeman in his random forest paper, and based on this idea, Fisher, Rudin, and Dominici proposed a model agnostic version of the feature importance, which they call model reliance. So the formal algorithm is presented on the screen. The input is a trained model F, a feature matrix X, a target vector Y, and an error measure or loss function L. The steps are simple. First, the error of the original model is estimated using the loss function. After that, for each feature J, a matrix X is generated by permuting feature J in the data X. This breaks the association between feature J and true outcome Y. Then the error EPerm is estimated based on the predictions of the permuted data. The permutation feature importance is calculated either using the ratio or the difference between the original error and the permuted error. Finally, the features are sorted in descending order based on the importance measure. The author suggested two alternatives instead of randomly shuffling the values of the feature. In the first one, the dataset is split in half, and the values of feature J of the two halves are swapped instead of permuting feature J. This acts as the same as permuting the values. In the figure, we can see an example. The values of feature 2 are split in two halves and swapped in the figure on the right. The values of the upper half are placed in the lower half of the newly generated dataset, and the values of the lower half are placed in the upper half of the generated dataset. The second alternative, which gives a more accurate estimate, consists in estimating the error of permuting feature J by pairing each instance with the value of feature J of each other instance, except with itself. This gives you a dataset of size n by n minus 1 to estimate the permutation error, but it might take a large amount of computation time. For example, in the figure, and if we take the first instance and working with feature 2, we pair each other instance values and create new records for the new dataset, except itself. If we do that, we will, with all records, we will end up with a 6-size dataset. This variant is suggested only if the estimates are desired to be very accurate, because it can use a lot of computation time. Now, let's discuss about using training or test data for computing the feature importance. For this, the author created an extreme example using a support vector machine. The model is trained using 200 instances of 50 random features plus the random target outcome. This means that there is no relationship between the variable and the true outcome. If the model learns any relationship, then it will overfit. And in fact, the SVM model did overfit on the training data. The mean absolute error for the training data is 0.29, and for the test data is 0.82, which is also the error of the best possible model that always predicts the mean outcome of 0, which is 0.78. In other words, the SVM model is useless. On the right, we can see the distribution of feature importance using the test data and the training data. The model overfit to the training data because in some way the importance was slightly greater than 1. However, the feature importance computed on the test data was close to 1, which means that all the features are actually unimportant. So, for giving some points to which data should we use, let us observe the partial dependency plot of feature x42, which is the most important feature according to the feature importance based on the training data. The plot shows that the predicted outcome depends on this feature, which should not be the case because all the values are random and independent. The value of the feature importance for training data is 1.21, but the value of feature importance for test data is almost 1, which means in reality the feature is not important. We know that estimating the error using training data in machine learning is a bad idea because the value is too optimistic, which means that the model seems to work better than it does in reality. So this supports the point of using the test data for measuring the importance measure. If the model error estimates based on training data are unreliable and the feature importance relies on the model error estimates, then the feature importance based on training data is also unreliable. However, there are a few points in favor of using training data, such as in practice, you use all the data for training because the datasets are very small. So there is no use the test data for computing the feature importance. When the data is small, we usually use cross-validation for estimating the error, which can also be a problem because the error is estimated only using a subset of the data on each iteration of the cross-validation process. In my opinion, the data that should be used is the test data, because the main point of a machine learning algorithm is to generate models that are able to generalize on unseen data. However, as the author also notes, it depends how you want to interpret the results of the feature importance measure. If you want to measure how much the feature contributes to the performance of the model on unseen data, then use test data. However, if you want to measure how much the model relies on each feature for making prediction, then use training data. Now let's check two sample results. The first one is the result of the model for predicting cervical cancer with a random forest. The loss is computed using 1 minus AUC, the area under the ROC curve. The interpretation is very easy. The greater the value, the greater the feature is important for the model. The vertical lines around the dots denotes the confidence level of the measurement. In this case, the age and hormonal contraceptive years are the most important features with a factor around 4.4. There are some features with values less than 1. which makes me think that those features even are harmful for the error estimate. The second example is for a support vector machine model used to predict bike counts. The loss function used is the mean absolute error. The most important feature, as we already saw in previous sections, are temperature and the days since 2011. In this example, the smallest number of a feature importance is 1, which is easy to interpret. The advantages of the model are that it has a nice interpretation, which is that it measures how the error of the model increases when the feature's information is destroyed. It also has a highly compressed and global insight. Also, using error ratio over error difference is good for comparing across different problems. It also takes into account all interaction between features because by permuting the feature, the interaction effects with other features is also destroyed. Finally, it does not require retraining the model, which saves a lot of computation time. The disadvantages of the permutation feature importance are that first, it is very unclear whether you should use training or test data to compute the feature importance, as it was discussed before. The permutation feature importance is linked to the error of the model, which in some cases might not be what you need. In some cases, you might prefer to know how much the model's output varies for a feature without considering what it means for the performance. For example, if you want to find out how robust your model's output is when someone manipulates the features. Also, the permutation feature importance depends on shuffling the feature, which adds randomness to the measurement. When the permutation is repeated, the results might vary greatly. Repeating the permutation and averaging the importance measures over repetitions makes the measure more stable, but increases the time of computation. If features are correlated, the permutation feature importance can be biased by unrealistic data instances. The permutation of features produces unlikely data instances when two or more features are correlated. When they are positively correlated, like height and weight of a person, when the features are shuffled, the new created instances are unlikely or even physically impossible. For example, a 2 meters person weighing just 30 kilograms. Yet, these new instances are used to measure the importance. Finally, the examples presented in this slide were created using the IMLR package, which stands for Interpretable Machine Learning. It also has other methods such as partial dependency plots, accumulated local effects plots, and individual conditional expectation curves. Additionally, it also comes with line and Shapley value functions. As an alternative, there is another method called PIMP, Permutation Importance, which also provides p-value for the importance. Thank you very much.